shape.
Okay, thanks.
All right, I think that's all the time we have. Thanks again, Natalie, for that great talk. And again, if you want to sign up to talk with Natalie later, feel free to do so. All right, so next up we have Chintan Shah. So Chintan obtained his bachelor's and master's in physics from MS University of Baroda in India in 2011. After working as an assistant scientist at Aditya SST tokamak facilities as the Institute for Plasma Research for a year in India, he moved to Germany to obtain his PhD from Heidelberg University. He received his PhD in 2015, where his focus was on the development of X-ray Compton polarimeters and on implementing techniques to study plasma anisotropies. Later, Chintan joined as a postdoctoral scientist at Max Planck Institute for Nuclear Physics in Heidelberg, Germany, where his primary focus was on laboratory astrophysics experiments with electron beam ion traps, or EBITS, to study underlying atomic processes responsible for the X-ray line formation, such as collisional excitation, dielectronic recombination, and charge exchange. Chintan's present interests at NASA Goddard include performing high-resolution laboratory astrophysics experiments with state-of-the-art X-ray transition edge sensor microcalorimeters to benchmark atomic theories and provide empirical data to improve present spectral models. And these will be critical in interpreting the high-resolution X-ray spectra that current and future missions such as CRISM and Athena will yield. So today he'll be talking to us about laboratory X-ray astrophysics experiments with EBITS and synchrotron radiation. So with that, over to you, Chintan.
Okay. So do you see my screen?
Yep, we see it.
Okay. Just a second. Yeah, so thank you for the introduction, Amy. So I think Natalie covered a lot of ground for me for this talk, actually. So the first part of this talk was kind of laboratory X-ray astrophysics experiment with electron beam ion traps. I think Natalie covered most of it, and then I will try to cover some of the experiments that we did in collaboration with the synchrotron radiation. So most of the example that Natalie gave is so-called like a classical spectroscopy that we could do using the EBIT, where electron beam actually drives the excitation, ionization, and the recombination processes actually. And if we can change this by using the X-ray laser from synchrotron or free electron laser, where we use EBIT just to produce and trap the highly charged ions. And then we use this X-ray laser and we can select the laser wavelength using those monochromator, and then we can photo excite those ions. And one of the key advantage of those kind of experiment is that it produces purely photonic excitation, which suppresses most of the uncertainty from the collisional excitation. And one of the example that I'm going to give you in the next slides. So the very first example that I want to cover is this iron 16 plus line emission problem, which is lingering around from last 3 or 4 decades. I think many of you are aware of it. So this is one typical spectrum, L-shell spectrum observed by Chandra and XMM Newton. You see the flux as a function of wavelength, and in this range 14 to 18 angstrom, you see those strong lines which are from iron 16 plus. They are the strongest emitter of soft X-ray lines, and you see those lines. Strongest line is 3C. It's a resonance line along with this 3D intercombination line. These are like a 2p to 3D line complex, and you also have 2p to 3s line complex, which contains also the intercombination line and the forbidden line. And the line ratios of this resonance to intercombination, or the line ratio between this 2p to 3D complex with this forbidden line complex, actually can give you a crucial information on the plasma temperature, density, velocity, and plasma opacities, and so on. However, what we see in last 40 years is that this intensity ratios of line 3C and 3D are consistently in disagreement with all the calculations in the model. So what you see here, these are the EBIT measurement band. This is a Princeton tokamak. These are some astrophysical observations from the sun and Capella, and you have this grayish square box, which are calculations in the model, and you can see that most of the calculations are consistently higher than what laboratory or the astrophysical observations can show. And not only for 3C and 3D, but also this another forbidden line complex 3S, which consists of this M2 line with the ratio with the resonance line 3C, also shows somewhat disagreement. So here you see this orange and blue and magenta. These are all the astrophysical observations. This is the tokamak experiment, and these are different models. In the model, if we only consider iron 16 plus, it produces this dash curve. And once you include actually the dielectronic recombination, which affects the lower temperature actually, so then it lowers down the line ratios, and basically this is epic and this is specs. And recently we actually corrected the cross sections in the specs with the EBIT measurement, which produced this band. So it is kind of in agreement with the previous one. So yeah, so we see this this disagreement with the astrophysical observations. So as Natalie mentioned, that with the EBIT, you can measure this individual atomic processes, their wavelengths and respective cross sections. And those iron 16 plus lines can be formed in the combination with electron impact direct excitation, dielectronic recombination, resonant excitation, and so on. And from last 2 or 3 decades, there are several experiments have been performed at different EBITS and the tokamak. And one of the recent experiment was performed in Heidelberg. So what you see here is these are the, just a second, oh, it's not going. Oh, okay. So these are the dielectronic recombination resonances from line 3C. So what you see here is the cross sections on the y-axis, and these are the electron beam energy axis. So you see different resonances from dielectronic recombination, and the blue curve is the distorted wave calculations from flexible atomic code. We find kind of good agreement up to some point, and when you go at higher energy close to the direct excitation threshold, we started seeing huge disagreement for dielectronic recombination, and this disagreement also continues here at the higher electron beam energy with the direct excitation and the resonant excitation. So what we see that the theory actually over predicts by 20% some of the cross sections of DR as well as the resonant and direct excitation. We measured the same way the 3S line, which contains this forbidden line. We find a good agreement, but one of the interesting thing was that, well, the 3S emission was fully dominated with the resonant excitation, and the cascades from different shells as well as from higher end shells. So it is very necessary to include those resonant excitation as well as the cascades from very high end into your model to predict those cross sections well. So this still doesn't give an answer that why do we see this 20% difference with the collisional excitation cross sections. So we went further one more step to measure the oscillator strength. So oscillator strength, as we all know, that this is just a probability of absorption or emission of photon given in the electronic transition. So we could actually measure the oscillator strength, which is kind of proportional also to the collision strength of 3C and 3D. So this was the first campaign that we did at LCLS. This is the world's first free electron laser at Stanford. And without going into details, this is a huge 4-kilometer long accelerator building, and here near to the close experimental hall, we actually parked our EBIT at soft X-ray hutch actually. And this is how it looks like. So the photon beam from LCLS comes from here, and this is our center of the trap. This is a Heidelberg flash EBIT actually, and we trapped ion here and photo excite them. And the measurement technique is the same as I mentioned in the beginning. So we simply scan the monochromator, and then we photo excite ions and measure the fluorescence. So this is what you see here at the left actually. So it's a fluorescence, photon energy, and the intensities are measured by this detector, and the free electron laser photon energy that is given by scanning this monochromator. So you scan across 812 and 825, you get 3C and 3D photo excited, and the intensity here intensities here are proportional to the oscillator strength of those lines or the Einstein coefficients of those lines. So you simply take the intensity ratio of 3C and 3D, which gives you the oscillator strength. So this is our experiment found out. So 2.6 plus or minus 0.2, and the rest of the calculations available at that time showed values above 3.5, and our experiment was like 3 sigma away from the best theory. So we concluded that, well, the inaccurately predicted oscillator strength in the theory are kind of a root cause of the long-standing discrepancy. However, later on, there were several papers came and which objected our measurement or gave some thoughts to our measurement, and which includes two main reasons. One of the main reason is the nonlinear dynamical effect, which could affect the line 3C and 3D ratio. So just to give you an example, so here what you see, excited state population as a function of pulse duration. So this pulse duration are like coming from the XFEL, X-ray free electron laser. So when you have very high intensities of 10 to the 12 volts per square centimeter and with very small pulses, the 3C and 3D, the upper state level population of 3C and 3D may not reach to the equilibrium. And in our experiment, we actually honestly did not know what is the pulse duration and so on. These were like the very first few years of the LCLS working actually. So, and the second reason was the population transfer. So this is between the iron 15 plus and iron 16 plus. So I talked about line 3D, but now iron 15 plus line C, which is very, very close to line 3D. And that has a very strong autoionization channel. So you have a radiative channel, but there is an autoionization channel which is continuously feeding the upper state, the population of line 3D actually. So we have to take care of both of these things in the next experiment. So this is the experiment we did at Petra 3 in Hamburg. So this is the synchrotron ring actually, and there are several experimental hall in this blue building. We parked our EBIT at one of the experimental hutch. It's called PO4. And here you see this significantly small EBIT. This is our recently developed new generation of EBIT called mini EBIT or tabletop EBIT, which has the permanent magnets actually, which can produce magnetic field up to 1 Tesla and can also produce very highly charged ions up to iron 24 plus. And one of the key reason to use such EBIT is that it has an off-axis gun, which means that the photon beam can simply pass through the EBIT. This is what is shown here in photoexcite band. So our EBIT can simply sit as a parasite in the beam line actually and continuously make the measurement. So here the synchrotron photon beam, which is very weak actually, only 10 to the 5 volts per centimeter square, and also the pulse duration are in less than nanoseconds, so we do not expect any nonlinear effect. And for the population transfer, actually, we need to improve the resolution. So this is the current resolution that we had, the resolution that we had at LCLS, roughly 1 EV resolution at 812. And also it can be compared with the Chandra high energy transmission grating, which has a somewhat similar energy resolution. And we improved this resolution by almost factor of 8. So with this improvement, actually, you can actually resolve this line C and line 3D simultaneously. That means like now we do not need to take care of those population transfer actually, or we can always observe the intensity ratio between line C and 3D to understand the population transfer. So now the measurement technique at the synchrotron was same as for electron laser. We simply select our energy with this mirror and grating, the monochromator box, and photoexcite those ion, and this is what we see. So this is line C and 3D, barely apart with only 150 millielectron volt that we could resolve now, and line 3C, simply you take the intensity ratio of line 3C and 3D and get the oscillator strength ratio. And this is what we get, 3.1 plus or minus 0.1. And we compare with different experiment in agreement with the tokamak and the EBIT experiment. Then we also had several astrophysical observations with the different temperatures. We have like a large band. We compare with the different databases available at that time, and this was in 2018. And the oscillator strength ratio in the database were in disagreement, as well as different theories available from the literature. and our own calculations that we did with the supercomputers and very large scale calculations with millions of configurations, we still found out that the theory is converging around 3.55 and our experiment was at 3.1. So we still find a disagreement. So the result from this campaign was that, well, yes, we are reinstating this long-standing problem with even better discrepancy, phi sigma, and the statistical uncertainty is too low, like 3%, statistical and systematic. So we thought that the low oscillator strength are still a root cause of this problem. So then we thought that what is next for the iron 16 plus problem? Can we actually measure, instead of the line intensity ratios, can we actually measure the individual line strength or individual line natural line widths of line 3C and 3D? And yes, we actually did. We improved a lot signal to noise ratio. Then we made a lot of diagnostics to actually continuously monitor the ion abundances. We also improved our X-ray energy resolution that I'm going to show. So this was our nominal setup basically. So X-rays come here, photo excite, we measure with the X-rays, and then we added several new diagnostics. So now with this new setup, what happens that the trapped ion are continuously being monitored with this electrostatic bender and ion detector, so we can actually know that what kind of charge states that we have in the EBIT. We can continuously monitor their intensities. Then the photon beam leaves this electrostatic bender, passes through this wire mesh where we actually continuously also monitor the intensity of incoming X-rays. Then those X-rays are actually impinged on the gold foil, and then it emit 4F electron, like photoelectrons, which are kind of analyzed by this photoelectron spectrometer in this hemisphere basically, and detected by MCP. So this is a new setup, and with this setup actually we improved this much from 2018 to 2020. So you could see again, this is LCLS orange, this is 2012. In 2018 we were here, this green curve, very bad signal to noise ratio, and then we improved further in 2019, improved even further in 2020, and similarly we improved our resolution to 20,000 from 8,000 actually. So with this kind of resolution, now you started seeing those effect of natural line width. So here you can see the line 3C if you are modeling with only Gaussian function, and if you are using Voigt, which is the convolution of Gaussian and Lorentzian, function, then you get this red curve, and you can see because of this Lorentzian line width, which is inherent to the natural line width of 3C, we see those difference in the intensity between two models. So with this, we measured at this resolution, we measured simultaneously several times iron 15 plus line B and C, and again line 3C and 3D. We can continuously monitor the population transfer, as well as the resolution is good enough to fit with the Voigt profile, 3D and 3C both. And then we found out that we are already at 3.5. So now our experiment is now in agreement with all of the theory, ranging from 1990s actually to our own calculation, very recent calculation done by Safronova last year. So now all the theories are in agreement, although the tokamak and the EBIT experiments are now in disagreement actually, including our previous experiment. So what we think that particularly about this collision experiment, EBIT and the tokamak, that those observations might have been hampered with the line C, which is continuously feeding line 3D, and the EBIT cannot produce single charge states. And again, tokamak is also, EBIT and tokamak both has a distribution of charge state instead of one charge state. So you need to monitor continuously iron 15 plus and 16 plus simultaneously. So this could be an issue with the previous experiment. There could be many other more reasons, but from the oscillator strength point of view, now we are in agreement with the theory. So what are the improvements that we did in terms of number? We went from 8,000 to 20,000 resolving power, signal to noise ratio from 0.05 to 45, which reduced also the statistical uncertainty from 2.6% to 0.6% basically. And again, the oscillator strength ratio also climbed up from 3.1 to 3.51, now in completely agreement. So what are my final remarks for this for this problem? That with our several improvements in our experimental setup, and we started quantifying the effects which are very far from the center of the line, especially this Lorentzian wings, which can be from the natural line width of the transition 3C. And also there is a pseudo Lorentzian type of instrumental profile. You model both things very well, and then you can recover the intensity. And once you recover those intensity, you take the line ratio of 3C and 3D, and finally theory and experiments are in agreement actually. I would give another example, but I would go very quickly now. So there is also somewhat an issue with the atomic oxygen velocity in the interstellar medium. I think many of you know this spectrum. This is a Chandra observed spectrum. And in this spectrum, you see this two strong line, which is absorption line from atomic oxygen. This is 2p1s transition around 23.5 angstrom. In terms of energy, Chandra observed at 527.4 eV, and XMM observed around 527.3 eV. But then the controversy started when there was a high resolution lab experiment done at Advanced Light Source in Berkeley. They have measured the atomic oxygen wavelength, which was around 526.8 electron volt. And if you compare this laboratory rest energy with the line of sight averaged energy from Chandra and XMM, the difference was 500 to 600 milli-electron volt. And if this difference is due to the Doppler, then it will also lead to a somewhat dubious conclusion that oxygen is moving away from us basically at the speed of 300 kilometers per second. So we decided to investigate this problem and dig a little bit further that how the calibration was done. So at ALS, the atomic oxygen was calibrated using the molecular oxygen. So the ALS beamline was actually calibrated with the molecular oxygen Rydberg series, which was calibrated from some numbers from older paper from inertial absorption, and that was calibrated using something else, and so on. So there was a chain of actually calibration which might have actually created a problem with the atomic oxygen at the laboratory. So what we decided, we wanted to cut off all those steps. We simply use the highly charged ions from our EBIT to calibrate the synchrotron photon beam, and then we could measure the molecular oxygen Rydberg series, and in return we can also recalibrate the atomic oxygen. So this was our setup in Berlin. The photon beam comes from here. This is our tiny EBIT. There are several people working so hard. The setup, basically the photon beam passes through our EBIT, excites the nitrogen and oxygen ions actually. We measured this with the X-ray detector, and then the photon beam passes through the gas cell, which is filled with the oxygen, molecular oxygen. It photoionized by the incoming X-rays, and we measure the photoions. So this is the spectrum from the EBIT actually. So here you have nitrogen 5+, hydrogen like nitrogen, helium like nitrogen 5+. So one is 5p, 6p, and 7p transitions actually. These transitions are very well known theoretically. They can be calculated to the subparts per million accuracy actually. So we could precisely calibrate the synchrotron beamline, and then with this gas cell we measured the Rydberg series. So this is the oxygen Rydberg series represented as a black curve, and this was the line which the ALS actually used to calibrate their beamline. And what we see, the difference between the ALS and BESI was the systematic difference of around 500 milli-electron volt, and to be precise in the number, the difference was 0.47 plus or minus 0.06 electron volt. And now if you apply this difference to the atomic oxygen, basically, then the oxygen 1s2p laboratory value agrees very well with the XMM and the Chandra observations. And then it also, we can say that, of course, as expected, the neutral oxygen is not moving at the speed of 300 kilometers per second. The last example I will give, which is the iron M shell UTA, the unresolved transition array, which we started investigating in just 2 weeks before we had a beam time in Hamburg. So I will show you some of the result. So this is again a spectrum from Chandra. in the range of 15 angstrom to 17.5 angstrom. These are all strong absorption line from iron 16 plus to iron 6 plus and oxygen 7 and 6 plus. This black curve, what you see here is the model, very old model from the Hewlett calculation. And then after that, Ming-Fang actually had a somewhat more precise actually many body perturbation theory compared to Hewlett, which is called configuration interaction. And they found out that for each charge states, there is a systematic difference leading from 15 to 45 milliangstrom. And if we convert it to the energy, this is about 1 eV at 800 electron volt. So we also decided to measure this thing in the laboratory because there are no laboratory measurement. So with the same setup, actually, we measure this thing. So with the X-ray detectors, actually, we can measure the fluorescence, which is kind of representing like proportional to the radiative rates of the transition. And with the ion detector, actually, we can also measure the autoionizing transitions. So these are all the autoionizing transition from the iron 13 plus, making it iron 14 plus actually. So we could measure this both things actually, and these are the preliminary measurement just 3 weeks back from 13 plus, 12 plus, 11 plus, and 10 plus, 9 plus. These are all fluorescent measurement representing radiative part of the transition, and this is the autoionizing part of the transition. These are also a different transition. So these are like a lower charge stage. We are also planning to go down to 5 plus and 6 plus and 7 plus, covering range below up to 700 actually electron volt. And we could also do the same measurement with the K shell actually. This is an example spectrum also measured in 2020 with Petra 3 at DAISY. We could measure now K alpha transitions from 24 plus to down to 19 plus, as well as we could see all those charge states in also K beta, 24 plus, 23 plus, and so on to the 19 plus actually. So what else we could measure? We could measure a couple of things like I have shown you. Photoionization can be measured. We could measure precise resonant transitions. We could measure Lyman series of the hydrogen like nitrogen, oxygen, and fluorine ion, very useful to calibrate the beamline. We can measure the K alpha transitions, K shell, L shell both. We can also measure the polarization. We can measure line width, branching ratio, and so on. And all of this work has been done by many people. And these are the names. And I would like to thank you for your attention.
Oh, thanks for that great talk. I know we're pretty much out of time, but if anyone wants to stick around and has a question or two, that'd be the time to ask. So I actually have a question.
Yeah.
I've seen in some of your papers that somehow you get the electron beam energy distribution down to like 5 eV.
Yeah.
How is it that you are able to do this?
This is mostly due to the evaporative cooling. So that can be done by two methods. Either you could inject, so at Livermore actually the evaporative cooling was usually done by injecting noble gas basically. So you have highly charged ions, but it is continuously actually cooled by the other gas which you are injecting. But what we do here at the in Heidelberg is that we actually lower down the axial trapping potential. So yeah, I don't have the figure, but yeah, we could lower down the axial potential like to 1 or 2 volts, and then ions are simply being trapped just within the space charge potential of the electron beam. And with that, actually, you can significantly reduce the width of the, for example, the dielectronic recombination or radiative recombination line widths, which are proportional to your electron beam energy resolution.
Wow. I'm guessing your count rate goes down pretty significantly though.
Yeah, so one of the thing, so at flash EBIT, we could actually get 5 eV, but even with this smaller EBIT, because the residual pressure in those EBITs are kind of bad because they are not cryogenic actually. So we get kind of direct cooling by the residual gas, and we could actually even achieve 2 electron volts now with
Wow.
this small EBITS. So we could really precisely measure all those resonance transition, which depends on the electron beam energy width.
Incredible. Looks like we have a comment here. It's really nice to have a resolution of oxygen wavelength issue and in favor of Chandra, of course, and the iron 3C3D problem. I agree. Yeah, really incredible work. So if we don't have any other questions, let's go ahead and thank our speakers again. 2 incredible talks, really nice. And we will see you all next week.
Yes.
Thank you.
Thank you very much.
Thank you very much.